Tonight we'll find out what these structures are, 3 compelling reasons why robot designers are starting to design robots this way, and why everyone should know something about this structure even if they never ever plan to design a robot. But first, this is a wonderful time for the structural geometry of Buckminster-Fuller. This is a Buckminster-Fullerene molecule on the left and a nanotube on the right there. There's a whole field of organic chemistry that's now based on these structures. But the most important thing that Fuller ever studied was actually invented by one of his students, Kenneth Snelson, back in 1948. Snelson is an Oregon native, and Snelson called these floating compression sculptures. Bucky picks a much sexier name for them. He called them tensegrity or tensional integrity structures. It's just a mashup of those 2 words together. So say that word to yourself right now. So this is the Corypa Bridge in Brisbane, Australia. Beautiful bridge that just opened up a couple months ago down there. So the critical definition of these things is that tension holds the parts apart. Now that's a very simple definition, but it has huge impacts on the structure. The most important of which is that the tension is actually bearing the load in the structure rather than the compression elements. This is very different from the way we learned to think about structure when we were growing up. We like to stack things on top of each other, jam Tinker Toys together, and when we started building really big things, we would weld and rivet them together. So we had rigid structures made that way. Tensegrity is different, and the structures are remarkably material efficient. They're used by aerospace applications. Nature is fiendish for efficiency. It uses it in all sorts of places, including our musculoskeletal structure. Second fact about these structures, they're remarkably energy efficient. If you put an egg in the center of one of these and dropped it to the ground, at the point of impact, the whole structure would be supporting the impact, not just the part between the egg and the ground. That's remarkable. Again, it's very different from the way our normal structures work. This is what I call the sweet spot for the tensegrity structure, where it moves very freely when it's balanced, but then it starts to get a little more rigid when it gets out of balance. So you can see this in your own body if you gently grab your earlobe and pull on it. You'll see it's very fluid when you start pulling, but if you continue to pull, it starts to get rigid. So that's the red line on the graph on the left there. Robots work in a very different way. They work in a linear fashion where it actually takes more work for a robot to move than it does for a biological structure. So robots that are designed using tensegrity will be more energy efficient or more green than they are right now. That's very important for the future. Third fact about these things, they're able to alter their global tension or their pre-stress on the fly. This bear has just cranked up his pre-stress, and everything within about 5 miles has also cranked up their pre-stress at this point. So these structures that can be relaxed or rigid are called viscoelastic, and that's the way we are. We can move in a very fluid-like fashion, or we can be very rigid, and we're one way or the other. So you can see several examples of this. One of them is cornstarch in water. You can walk across it. If you walk across it quickly, you can actually literally walk on the water. But if you stand still in one place, you'll sink. Same thing with a Tempur-Pedic bed. If you put your hand on it, you'll sink and make an impression. But if you slap it, you won't. So we love to crank up our tension in our bodies. We just had our national pre-stress holiday, otherwise known as Halloween. All sorts of outdoor activities we love to crank up our stress on, and some indoor activities we also like to crank up our pre-stress. Now, the opposite of this is body-mind disciplines, and those are all about lowering the stress in our body, balancing and aligning the structures that are there. You can go to classes to do this, if you're really smart like Kathy Sierra, you'll actually set up your workstation where you're balancing and lowering your tension all the time. So these are the qualities that future robots will have. Remarkably material efficient and energy efficient. Now the question for you, are you more like a 1.0 robot or a 2.0 robot? And we've got an exercise about that right now. So pick the word that most inspires or intrigues you from the list here right now, and then close your eyes. Now, what would be possible if you allowed your body to feel that way right now? Thank you. Here's your homework. And I also have slide notes online at floatingbones.com, robot.pdf. If you take this homework and run with it, if you really work at a regular practice of eliminating unnecessary tension, you will have remarkable results. Thank you very much.